It's a little bit hard, this question, because there's no diagram to help you with it. You've got to read it and imagine or draw what's going on. So engineers are designing a footbridge with a concrete slab, and they want to reinforce it with steel wires in it. So if we've got, here's our grass on one side of the bank, here's our grass on the other side of the bank, and they're going to put a footbridge along it like this. Now, as an exaggeration, it's going to be the force, the weight of the bridge acts from the centre of it, so it looks like that. So as an exaggeration, what's going to happen to this bridge is it's going to start sagging. Now, it won't sag this much, but this is just an exaggeration so we can see what's going on. Now, as it sags, the atoms near the top are going to be pushed together. That's curved on the side of the curve, so the atoms at the top are in compression. And at the bottom, the atoms are going to be stretched apart from each other, so the atoms in the bottom are going to be in tension. Now, concrete is weak in tension, so we have to put our steel wires down the bottom because they are strong in tension. So we'll put our steel wires down the bottom of the slab, one there, and another down the bottom here. That's to strengthen it. So which of these answers explains that? Where's the best place to put the steel wires? Near the top of the slab? No. Near the top of the slab? No. Near the bottom of the slab? Yes, because steel wires are strong in compression, but they are weak in tension. Now, the reason we put it down the bottom is because the steel wires are strong in tension. So that weak in tension must be wrong. Near the bottom of the slab, yes, because steel wires are weak in compression, but they are strong in tension. Yes. The engineers calculate the overall strength of the slab. To find that out, out to its breaking point. They find that out to its breaking point it has sufficient safety for the task. Alright, with the bridge in place, they test the slab with 3 times the design maximum. So this isn't necessarily the breaking point, but this is the maximum the bridge should be taking. But still within design strength, so it's still within breaking point. The bridge sags slightly with the load, as expected. However, when the load is removed, the bridge retains its sag. Why is this the case? This can be best explained using a stress-strain graph, just like in the earlier questions we've done in this exam. Stress-strain graph says we apply a stress to it or a force to it to test it, and what happens to the material? How does it stretch, or how does it compress? And most materials look like a straight section and then a curved section, like that. The design maximum for this will be at the end of the straight section. At the end of that straight section. At the end of the straight section, if you put anywhere, if you apply a force anywhere along here and you take that force off again, it goes back to its original shape. If you go past this limit and you apply a force past here, it doesn't go back to its original shape. So it's going to retain its sag. So it must have been that they've tested the material up around here somewhere. This point at the end of the straight section is called the elastic limit. So what's happened is they've tested it past this point. So which of these answers has that? Best explanation is that it has been extended past its breaking point. Well, no, its breaking point's out here, so it's not this one. It's been extended beyond its elastic limit. And there's its elastic limit, it's gone beyond that. That's the answer. Okay, large Young's modulus and small Young's modulus is just the steepness of this, which has nothing to do with retaining its sag. So our answer is B.